Okay, so a little more on sets. We have algebraic rules for sets, just like we do for numbers and lots of other things. So set union and set intersection are commutative, and that's awesome. So we can take A union B, that is, we can start with A and um, include the elements of B as well, or we can start with B and add in the elements of A, and either way we get the same thing. Same with intersection. We can start with A and remove the things that aren't in B, and we'll get the same thing as if we start with B and remove the things that aren't in A. Great. Associative laws tell us that if we're taking an extended union or extended intersection, it also doesn't matter whether we first add the things in B to A and then the additional things from C, or we take the union of B and C first and then find the union with A. We'll get the same thing. Same with intersection. We could find the things that are both in both A and B, and then the things that are also in C, do it in that order, or we can start first with the elements that are in B and C, and then look for the ones that are also in A. So very nice there. The distributive laws are also nice, but with distributive laws, because we've got multiple operations going on, we've got union and intersection, things get a little bit trickier. So I want to illustrate these laws with Venn diagrams. And so I've got kind of two things going on here. One is illustrating how the laws work. So I'm just going to actually draw a picture that I think should convince you that each of the laws is true. The other thing I'm illustrating is the process of using a Venn diagram to sort out kind of a complicated looking expression involving sets. Um, Venn diagrams have kind of like a sweet spot for them. If you have a really complicated set expression, it's probably going to be hard to draw a picture for it. And if it's really simple, you don't need one. But in sort of expressions with this level of complexity, which tend to be typical of examples we use to sort out potentially tricky things, Venn diagrams are your friend. Okay, so what I want to do is, first of all, just remind myself of what those distributive laws are. So the first one, the claim is that A union B intersect C is the same thing is as if I first take A intersect C, then B intersect C, and the union of those things. Okay, so what I want to do is just draw a Venn diagram for each side of the equation. And what we should find is that the uh, areas indicated are equal. So I'm drawing a Venn diagram. I'm always going to first draw my sample space, especially if I'm working with complements. I definitely want to have that sample space demarked so that I can see what's not in my sets. And then I'll just draw my sets, A, B, C. If you find yourself drawing Venn diagrams with, say, 3 sets, don't just start like randomly drawing circles and end up with something that looks like the Olympic symbol or something like that. Because you won't be able to find the things that you need. What I was doing here is I was being careful to let every possible intersection be indicated. So I've got A overlapping with both B and C, and uh, those things overlapping as well. Okay, so I've got a nice general Venn diagram that I'm starting with here. Okay, and I'm going to use color to sort of denote the sequence of operations here. So let's use yellow to denote A union B. Okay, so A union B is everything in A, all this right here, everything in B, all that right there. And then what we're going to find is the intersection of that with C. So let's make that pink. Okay, so now I'm looking at intersection. It's got to be both in the yellow and in C. So this area, and I'm actually going to highlight the intersection symbol here. on the board. 2 because that's what I'm coloring pink there. Okay, lovely. So the claim is, if I do the intersection and union in a different order, I'll find this same area. So let's see. Still my sample space. Still got my A, my B, my C. Here they are. Okay, so now I'm going to use goal to be A intersect C. Okay, so that's in A and in C, this. And I'll use blue to denote B intersect C here. And now I'm going to take the union of that. Okay, and yes, indeed, I get the same thing. Yay, just like I said. Isn't that great? All right. Same story for the other distributive law here. So the other one, the claim is that A intersect B union C is the same thing as A union C intersect A union B. Draw it the same way. Sets A, B, C, and so first I want A intersect B. So A intersect B, that's this kind of lens-shaped area here. And then I want to take the union of that with C. Okay, so just as I did before, here's all my C, and the union says it can either be either in C or in A intersect B. So I get this circle with kind of a tail on it here. Okay, so now if I do things in the other order here, C, sorry, my sets are getting a little bit messy here. A, B, C, this is my sample space. Starting with A union C, we'll make it pink, like this. And A union B, just A union C means it's in either one or the other. And did I write that wrong? Look, I wrote that wrong. Okay, sorry folks, we're gonna do some erasing here. I guess while I am erasing this, I'll elaborate on something that I do often enough that you'll learn to catch me on it. Some of you are probably prone to this kind of mistake too. It's kind of an autopilot type of mistake here. What I wrote here was wrong. Okay, if you go back and look at the notes, A intersect B union C, what you want to do is distribute the union C to both the A and the B, and I didn't do that. Okay, what I've got here that is wrong, this should be B union C. Okay, let me correct it here. So this was wrong all along. Hopefully everybody now has noticed that it's wrong and corrected it in their own notes. And what is right here, okay, I'm gonna erase now, I'm gonna write the right thing. What this should be is, it's A intersect B union C is A union C intersect B union C. Okay. And as I said, it's a kind of mistake that is easy to make when you just start like writing things according to some pattern that your brain makes up that isn't the right thing. But the good news is, and maybe this underscores my point about Venn diagrams, I wrote it like just fine to me, went along my way, but when I started to do the Venn diagram, that's where I found my mistake. So another good thing that you can use Venn diagrams for is checking your logic. All right. all that to get back to my A, my B, my C. There's my A, my B, my C. Just as we did before, we'll make A union C, this whole area. And now we need blue for B union C, means it's either in B or it's in C. Okay, and then what we need to put them together is we need the places that are shaded both pink and blue. Okay, and it's this whole circle plus the little spiky thing sticking up. Okay, so indeed, as long as we write this side correctly, we do indeed get the same answer there. So little side bar there to illustrate using Venn diagrams. Maybe I illustrated it more effectively than I thought I was going to. A great way to find your mistakes. What we were doing was just illustrating the two distributive laws that you can distribute intersections and unions in either order. Okay. The other, you might think of them sort of as distributive laws that are combining negation with intersection or negation with union are called De Morgan's laws. Okay, so if we have the complement of an intersection is the union of the complements, and the complement of the union is the intersection of the complements. Okay, so that's just weird enough that let's illustrate those with some examples that I'll talk through here. Okay, so as an example of the first law, so what I'm thinking about here is A intersect B complement. The claim is that that is A intersect B union B intersect C. Okay, so I'm going to illustrate these more with examples than Venn diagrams. And the example I have in mind here is like electoral canvassing. So you're knocking on doors trying to get out the vote. And what you want to do is you want to knock on doors for people who satisfy two criteria. Okay, one is they haven't voted yet, and B is they are likely to support my candidate. Okay. So the people I want to, whose doors I want to knock on, have both of those properties. The houses I skip, that's the complement, are, what are they? Either the people who have already voted, okay, that's water under the bridge here, they've already voted, or not going to support my guy. Okay, so in that kind of concrete example, it's easy to see how if the things you're looking for have two properties they need to have, they need to be in A and they need to be in B, the things you can skip them if they fail to have either one. Okay, so the negation of an intersection is the union of the individual negations, right? Okay, so second example will also be from electoral politics here. So we want the complement of a union here. Okay, and so here, another kind of vaguely election-oriented example, but now I'm thinking not of a canvasser, but say of an organized group who's thinking about interviewing candidates, like say this would be at the nomination stage when there's a lot of candidates, the group's thinking, okay, well, which candidates are worth interviewing for a potential endorsement, okay? And so many groups would say you interview if either they're likely to win, okay, because you want to have, they're likely to win, you want to develop a relationship with them, okay? Or, okay, so, or there's the union here. They are already an ally. Okay, so if somebody's running and you don't really think that they're going to win, but they are actually really on your side, they came out of the union you're a part of or something like that, you want to interview them anyway. So you want to interview them if either thing holds. Okay, who do you say no to? Who are we? We take the compliment, that's what we're doing. Who do we not want to interview? It's the people who are both unlikely to win and not an ally. Okay, so that is, they are both not real contenders here and not really going to champion our cause there. Okay, so again, I'm illustrating here, I think, another technique, not just with sets, but just in general, with something that seems complicated when it's written in symbols. Figuring out a story that fits the symbols will sometimes make the logic, make you appreciate in kind of a visceral, memorable way that the mathematical symbols by themselves might not necessarily create. Okay, so yeah, that's De Morgan's laws. I describe those same little scenarios in the written notes there. And then I also just want to go through a couple of some very related but useful terms. It's over and over again, we're going to be asking ourselves whether sets are mutually exclusive or not. Mutually exclusive just means they have an empty intersection. Nothing in A is in B. Nothing in B is in A. They're mutually exclusive. That is a helpful fact for us to know, especially once we start assigning probabilities to them. Building on the idea of mutual exclusivity is the idea of a partition. Okay, so for a partition, we're taking some set and we're dividing it into mutually exclusive and exhaustive subsets. Okay, so this is kind of, we're going to put each element in the set in exactly one of the partitioning sets. So everything that is in B is in one of the A's. Okay, so I've got that written here. And none of the A's overlap. Thinking about that government formation example that we had, we could partition the set of governments into, I'll go ahead and write this. Remember when we had, it's interesting, let's get a real pen here. A set of governments that could be formed after an election. It could be a coalition of party A and B, party B and C, party A and C, A, B, C, A, B, and C. Okay, we could partition that, like we might partition it into an event that we might call a minimum winning coalition. So these are, that's a phrase from coalition theory that denotes something that's got a majority but no excess members. So this we're thinking of like no excess parties. So the minimum winning coalitions would be A, B, B, C, C. Supermajority government would be A, B, C, and minority government would be A, B, C. Okay. Just to refresh your memory, in the example that we had before, party A had 40%, B had 40%, and C had 20%. So these minimum winning coalitions, you might just want to think of those as like majority governments, majority with no excess parties. All this to say here is that these three events, these three sets, partition S, okay? But another way we might want to think about S, about dividing up S, is in terms of what parties are in government, okay? So if we have the set of governments that include party A, that would be A, wouldn't be BC because A is not in that one. It would be AB, AC, ABC, and A. Okay, those are all the governments here that include party A. And you know, we can do the same thing for party B, is in AB, it's in BC, it's in ABC, and it's in B. And the set of governments that include party C would be AC, BC, ABC, and C. And my point here is these three sets are not a partition. Okay, they're not a partition because there's overlap. The intersections are not empty. AB is in both of these. ABC is in all of them. So they don't have these empty intersections. Partitions are super helpful, right? If you're going to divide something up, it's a really nice, neat, tidy way to divide things up, is to include everything and just have it in one spot. And when we can get to partitions, we are always happy because it just makes it easy to keep track of our events. All right. Final related idea, I call it a divide and conquer rule. We're going to see a bunch of divide and conquer rules because this basic logic is going to appear with probabilities and expected values and probably some other places as well here. But just right now, thinking about sets, for any set A, you can always partition A in terms of B. Okay, A always equals the part of A that intersects B union the part of A that does not intersect B. Okay, so I'm just drawing one little Venn diagram here. A, and B. You can always partition A in terms of the part of A that overlaps with B. That's this part, and the part that doesn't. Okay, and that's just super useful when we're trying to figure out whether something's true about events or about the probabilities assigned to them, is to know that we can break down events in this way. So last thing that I'll leave you with, just reinforcing that idea of Venn diagrams being helpful for understanding sets and for checking basic logic in a visual way. Highly recommend them. Don't get too carried away because they're kind of fun. You can waste a lot of time with them, but if you want to fool around with a goofy Venn diagram, here's one that I found on the internet that has lots of people, and it's its own little interesting Rorschach test. I mean, there's some of these people I know who they are. I agree that Willie Nelson is a picker and a toker, but not as much of a grinner as Jerry Garcia is. Some of these other people down here, the jokers and the smokers, I'm not even sure who Dennis Leary, Bill Hicks, these guys are, but I'll take their word for it. Anyway, if you want to fool around with a Venn diagram, here's one, even with some questions about it. So that's our quick overview of set theory. On to actual probability theory in the next lesson. So I'll see you then.